Hi, this is Kevin Trainer. Welcome to my lecture on Chapter 9 of the third edition of the Zelle Python programming book. Chapter 9 is about simulation and design. And Chapter 9 is I think a pretty cool chapter. Okay, the simulation aspect is is important for a lot of reasons, but one of the reasons is it's really fun to build games with your newly found skill of computer programming. I think back to when I learned to program well over 40 years ago, and the first things that I wanted to build were games. In these days, there are a lot of books on how to build games with all kinds of programming tools, including Python. So, what we're going to simulate is a game, and that perhaps you'll take that as some inspiration as to something you might want to do on your own after the course is over. The next thing is that the simulation that they do, they really go about it in kind of a purposeful way. They try to design, the author, I say they, but John Zelle, he tries to design the program in a pretty thoughtful way. So this is the first time that we'll have talked about program design in as thoughtful and complete a way. And I think this is going to be important to you because when you decide that you want to build a program that's got some a complexity to it, like a game, if you decided that you wanted to create a game, well, then it's probably best to not just sort of go at it willy nilly. It's probably best to come up with a thoughtful design and then implement it. And this is, I think, a really good walkthrough of that kind of approach. Um, and it's a fun chapter. So here we go. I'm going to break it into two parts. We're going to break about halfway. So there'll be a part one of the lecture and a part two. This is part one. Something that I've done and that you may want to do is I've gone and found the code from the textbook, which is the program that he builds during the chapter. And what he simulates is a racquetball game. So he calls the program R-Ball, which of course I think is a horrible program name. Why not racquetball? Uh, he and I have this sort of ongoing conflict over the naming of things. I want you to take after me, not after him. Okay. And what I kind of like is that it's uh, uh, what I like is that the program can be just easily run. What I did it is I went and put it in my Frankenstein project, which is where I put all my experimental programs. So let's give it a run here before we even start with the slides. Okay. So let's see. This program simulates a game of racquetball between two players called A and B. The abilities of each player are indicated by the probability, a number between 0 and 1, that the player wins the point when serving. So if a player has a 50% chance of winning their serve on average, then the number would be zero point 0.5. Player A always has the first serve. what is the probability player A wins a serve? Well, let's say it's about 0.6, 60%. And what's the probability that player B wins a serve? Let's say it's about 50%. Okay. How many games would we like to simulate? Okay. What they do is we run this game over and over again and we see how many times each of the players win. Okay, so let's say 200 games. And it says games simulated 200, wins for A 160, wins for B 40. So what is kind of interesting is that even though the difference between their ability to win their serve is only different by which seems like a small amount, the difference between 50% and 60%. When they play a bunch of games, the player with a higher skill wins 80% of the games, which is kind of surprising. I mean, you would think just, things averaging out, that the lesser player would do better than that. But it turns out that he doesn't. Okay? So I say find the program, load it up, run it, get familiar with it, and then come back here and we'll talk about it. Okay? Here we go. So why simulation? Well, simulation can get us the answer to a lot of problems in the real world by mathematical modeling. Okay? And sometimes these are things that are kind of hard to figure out through kind of analytical means, through just raw calculation. And even though you can describe the problem in some kind of a sense having to do with mathematical probabilities, it's not always easy to foresee the outcome. And so what we do in simulation is we run through the process, given the probabilities, and then we measure the outcomes, and we do it a lot of times really fast. And then, so we see the implications of the numbers that we chose for the kind of underlying probabilities. So, what do people use this for? Well, to predict the weather, to design aircraft, to create special effects for movies, all kinds of things. So there's lots of fun things that you can do. So here's the problem. I've already given you a peek ahead. We're going to come up with a racquetball simulation, and this fellow, Denny, he's not that much worse than his friend, but they play racquetball all the time, and he hardly ever wins. And he thinks, well, shouldn't he win more often, given the fact that he's not that bad? So his friend Susan says, well, why don't we write a simulation to see if only a slight differences in ability can cause such large differences in the scores, in the outcomes of the games. Now, we've already peeked ahead. We see it can. Okay, so probably Denny at the end of the chapter, when he knows what we know, he can probably go to bed not so sad. Because this is what happens to people when they're learning the game. Even if they're just a little bit worse, they're going to lose most of the time. How about that? Okay, so we described the racquetball game. It's 2 players. They use a racket to hit a ball in a 4-walled court. One player starts the game by putting the ball in motion, serving the ball. Players try to alternate hitting the ball to keep it in play, referred to as a rally. The rally ends when one player fails to get to hit a legal shot. Okay, and I haven't played racquetball in a long time, but I think that's a pretty good description. The player who misses the shot loses the rally. If the loser is the player who served, the service passes to the other player. If the server wins the rally, a point is awarded. Players can only score points doing their own service. And this is true of, uh, a number of games, including racquetball. So if you're serving, if you win the point, then you win. If you serve and you win the rally, then you win a point. If you're not serving and you win a rally, then you win the serve. Then you have to win another rally on your serve to get a point. The first player to reach 15 points wins the game. And there's no chance to catch up. Okay, so I was kind of playing with the program a little while ago, and I realized that I was asking myself, would it be possible to get to 15 if 15 points for both of the players at the same time? And the fact is that's not possible, because as soon as the first one gets to 15, he or she wins the game. Okay? There's no chance to tie. And there's nothing that says that you have to win by two. Often that's the part of the rules that gives the other player the chance to tie. In our simulation, the ability level of the players will be represented by the probability that the player wins a rally when he or she serves. Example, players with a 60% probability win a point on 60% of their serves. And you would think if people were equally matched, okay, well then they probably would win as many as they would lose, and so their probability would be 0.50. Okay. The program will prompt the user to enter the service probability for both players and then simulate multiple games of racquetball. The program will then print a summary of the results. Okay, now one of the things that's really good about this as an example for me is that this isn't something you can do just in your head. Okay. One is it lends itself to simulation. You need to play it through a lot of times in order to get a reliable answer. Two is that there are a bunch of points to it. Who's serving? Who won the point? Who won that game? Blah blah blah. You have to keep score of the points in the game and the games in the series and all that kind of stuff. There's more than one thing going on at the same time, and that's probably a little more complex than some of the problems that we've done kind of earlier in the book. And it's just the kind of thing where you have to be thoughtful in your design. So we're going to analyze the problem and try to come up, try to make clear the specification or the requirements for this program. So on the input side, the program prompts for and gets the service probabilities of players A and B. The program then prompts for and gets the number of games to be simulated. Okay, and again, you want it to be a fairly high number. I think we did 200 in the example that I had, but when I ran it the time before, I think I did 2,000. Okay, it's amazing how fast these things actually run. We'll do some experimenting with that before we're done. Okay, output. Now, it's really important to think of any program or program part in terms of what's its input, what's its output. Okay, because as a user of the program, you're typically only interested in the output. You just want answers, okay? And in order to get the answers, you have to provide some inputs. And what it does with the inputs to create the outputs is interesting, but only so interesting because you're an end user, right? So we've just seen what the inputs are. More importantly, what outputs are we going to get back? So output. The program will provide a series of initial prompts such as the following. What's the probability that player A wins the serve? What's the probability that player B wins a server? They couldn't fix that typo. Sorry, wins a serve. How many games to simulate? Okay, the program puts out a nicely formatted report. This is after all the simulation is done, showing the numbers of games simulated and the number of wins and the winning percentage for each player. So the games simulated in this case, I guess we asked for 500. Wins for A, 268. Wins for B, 232. Those add up to 500. And then we show what the percentage is. And that's just a matter of doing the math. Okay? And it looks like we formatted them in kind of a pretty way as well. Okay. So here are some notes regarding the requirements here. All inputs are assumed to be legal numeric values. No error or validity checking is required. So if we were going to build this program for strangers or people who were going to pay for it, they would expect it to be more robust than this. Okay? We're only trying to kind of illustrate the overall program design and architecture. And we could spend more time assuring ourselves that we got proper inputs, but that's not what we're concentrating on in the current chapter. In each simulated game, player A serves first. I don't know if that's always the case in racquetball. I suspect not. But that makes our game easier to simulate. Okay, now, some background, okay? One of the things that we're learning about here is the computing approach to random numbers. Now, this is good for simulation, like we're doing now, but it's also really important for games of chance. And a lot of people like to write programs that, it's a blackjack game, or it's some kind of a dice game, or it's some other kind of card game. That's what got me hooked. I don't know what's going to hook you, but that's what hooked me. And of course, in order to do that, you need to simulate some kind of a chance outcome. Okay, so programming languages generate these random values. Okay, and we're going to see in a second that we call them more explicitly pseudo-random numbers. So when we say the player A wins 50% of the time, that doesn't mean that they win every other game. Rather, it's more like a coin toss. Overall, half the time the coin will come up heads. The other half the time it will come up tails. But for one coin toss, but one coin toss does not affect the next. It's possible to get 5 heads in a row. And statistics language, getting the same value in a coin toss multiple times in a row is called a run. So that would be a run of 5 heads. Many simulations require events to occur with a certain likelihood. These sorts of simulations are called Monte Carlo simulations because the results depends on chance, probability, and also because Monte Carlo is a place where they either used to or currently gamble, and they had games of chance, things like card and dice games. Okay. So, do you remember the chaos program from chapter one? I didn't really like that program, so I remember it all too well. The apparent randomness of the result came from repeatedly applying a function, a formula, to generate a sequence of numbers. A similar approach is used to generate random, technically pseudo-random numbers. So it's possible to write code, kind of like the code from chapter one, that it turns out a series of values that behave randomly. Okay? Are they truly random? No, they're not truly random. They're close enough to random for the purposes of simulations and games of chance, and so that's fine with us. So a pseudorandom number generator works by starting with a seed value. The value is given to a function to produce a random number. Okay, what's a seed value? Well, if in fact we had a fixed formula for generating random values, well, every time we called it, we would start the same sequence all over again. Okay, so if you use that to play some kind of a game, you'd always be playing the same game. You know, first you get a 2, then you get a 5, then you get a 3, then you get a 2. It's like, well, this is kind of boring. Okay, so if you provide the formula, the algorithm that generates these pseudorandom numbers, if you provide it an input value and you provide it a different one every time, well, then the first value is going to appear random to you, and then every experience that you have with the program that generates this series of numbers, it's going to look like it's truly random. They're not going to look like you're playing the same game over and over. So the value that we use to start this is called a seed value, and typically it's the current time or date. Okay. So the next time a random number is required, the current value is fed back into the function to produce a new number. The sequence of numbers appears to be random, but if you start the process over again with the same seed number, you'll get the same sequence of so-called random numbers. Python provides a library module that contains a number of functions for working with pseudo-random numbers. These functions derive an initial seed value from the computer's date and time when the module is loaded. So each time a program is run, a different sequence of random numbers is produced. The two functions of greatest interest are rand range and random. Okay, so in the package, in the module, the random module that we are importing, right? We are interested in two of the functions, rand range and random. Rand range is really helpful because typically, if in fact you've gotten the game bug, if I've gotten you kind of interested in this, let's say we want a process that looks like rolling a die. Okay, well, we're going to get a value between 1 and 6, right? If we're going to pick a card from a deck of normal playing cards, well, we're going to get one of 52 different cards, okay, if it's a full deck when we start. If we flip a coin, we're going to get either the value 1 or 2, okay? So what's really nice about the rand range function is you can get a random value back, and it is an integer in a range that we've already described. Now, you'll remember that ranges begin with the first of the numbers that you give, and the second of the numbers that you give is the first one that you don't want. So if you want values between 1 and 5, you say rand range 1 comma 6. Now, was this a silly way to design these things? Well, I think it was, but then again, I wasn't there. Okay, you just have to remember rand range 1, 6 gets you values between 1 and 5. So if we had a die, okay, if we were going to roll a die, okay, we would do rand range 1 comma 7. So then the highest value we would get back would be a 6, and the lowest would be a 1. Okay? And if we did rand range 5, 105, 5, it returns a multiple of 5 between 5 and 100 inclusive. So one of the nice things about this rand range is they use the semantics of the range function, which we know and either love or maybe don't love. Ranges go up to, but don't include the stopping value. Okay? So this is quite nice when we're trying to write some kind of simulation or some kind of a chance-oriented game. We can do rand range. Okay? So here it says each call to rand range generates a new pseudo-random int. So we call it once, we get 5, then we get 3, then 2, then 5, then 5, then 5, then 4. Okay? So what we expect is that if we do this a large number of times, okay, let's say we do it 10,000 times. If this is really behaving randomly, we would expect each of the values to come up 1/5 of the time. So let's say we did it 5,000 times. We would expect to get a 1 1,000 times, a 2 1,000 times, right? That's how we would expect that to happen. Now, does it turn out to be exactly that? No, but it's pretty close. And the number of iterations that you do it for, and then you tally the outcomes, the closer you get to what your theoretical expectations would be. Like here, we've only generated 1, 2, 3, 4, 5, 6, 7 values, and we got 4 5s. Well, that's doesn't seem so random. But if we did it instead of 7 times, if we did it 70,000 times, it would calm down. And when you looked at them in the aggregate, they would be random. Okay? Okay, so in fact, our author says the value 5 comes up over half the time, demonstrating the probabilistic nature of random numbers. Over time, the function will produce a uniform distribution, which means that all values will appear an approximately equal number of times. And like I say, you'll have to experiment with this a bit yourself, but in 10 iterations, it probably won't look so random. In 100, it'll look better. In 1,000, it'll look better. In 10,000, it'll look pretty darn good. In 100,000, it'll look really, really good. Okay, so that's the nature of probability. Okay, which is uh, a lot of times when people talk about probability, they talk about the law of large numbers, which means the law of a lot of instances. So if you have a random process and you do it a lot of times, you should expect things to come out um, in their kind of theoretical distribution. So if you have a fair coin and you flip it 1,000 times, you're going to expect to get about 500 heads and 500 tails. If you have a die that's a fair die and you roll it 1,000 times, you're going to expect to get one sixth of the time. You're going to expect to get each of the values about 1/6 of the time, and in a lot of rolls, something like 1,000 or 10,000 or 100,000, you're going to see this settle down and look just like it should. So the random function is used to generate pseudo-random floating point values. So this is going to be what we're going to use in this racquetball game because we're trying to express the probabilities as a decimal fraction between 0 and 1. So if it's 0, it's not likely at all. It's not going to happen. If it's 1, it's a sure thing. Okay, so we were saying that the probability that either a player would win their serve, we were saying for one it was 0.6, the other it was 0.5. So they were almost equally likely to win or lose their serve. Okay, they're approximately half the time. So the random function takes no parameters and it returns values uniformly distributed between 0 and 1, including 0 but excluding 1. Interesting. So we just go down to the Python console and we call random over and over again, and we can see a couple things. One is that we're getting back a real float, so we're getting a lot of digits. Okay, and the other one is that they're all higher than 0, although they theoretically could include 0, and they're lower than 1. And that's about all I want to say about those. So the racquetball simulation makes use of the random function to determine if a player has one serve. Suppose a player's service probability is 70% or zero point 0.7. If a player wins, if player wins a serve, then we're going to bump up the score by 1. We need to insert a probabilistic function that will succeed 70% of the time. In here, player wins serve. Okay, so we need to come up with an expression, probably using the function random, that is going to turn out to be true on average 70% of the time. How could we code that? Suppose we generate a random number between 0 and 1. Exactly 70% of the interval from 0 to 1 is to the left of 0.7. So 70% of the time the random number will be less than 0.7. And it would be greater than equal to 0.7 30% of the time. The equal goes on the upper end since the random number generator can produce 0 but not 1. You know he's a true mathematician when he's getting down to this kind of a level of granularity. Okay, if the variable prob represents the probability of winning the serve, not server, the condition random less than prob will succeed with the correct probability. So if prob is equal to 0.7 for a particular player, uh, the uh, the expression random less than prob is going to happen about 70% of the time. Okay? So the code that we can use for that, we could say if random, less than prob, bump up the score. So that's how we know they won the point. Okay? All right. Now we're about to get into top-down design. And I'm going to pause for a second to wet my whistle, and I'll be right back. Okay, so what is top-down design? Top-down design is it's a method of approaching the problem of designing a program that's been around. It was really coming into vogue when I got into programming, so it's been around more than 40 years. But it's still very popular, very useful, because it's it's a good idea. So in top-down design, a complex problem is expressed as a solution in terms of smaller, simpler problems. Okay? So we kind of think of the problem as a bit of a hierarchy. So when looked at from the top, we're looking at the whole problem, and then that's made up of sub problems. And then when we look at each of the sub problems, we can further divide them into sub problems. And when we get done, we have a tree or hierarchy of problem parts. And then we build a code for those problem parts, and we get a tree or hierarchy of code, and that becomes our program. So these smaller problems are then solved by expressing them in terms of smaller, simpler problems. This continues until the problems are trivial to solve. The little pieces are then put back together as a solution to the original problem. Okay, and it's a proven approach, right? You can look at the problem as a whole and say, I don't know how I'll ever solve that. But in this top-down approach, sometimes called functional decomposition, where you take the functions of the program and you break them apart. So you look at it as a whole, and then you divide that into parts, and you divide each of those into parts, and you keep dividing until the parts are, you look at them and go, I can code that. That's simple. I know how to do that. Okay, so that's what we're doing. Typically, a program uses the input process output pattern, which is to say at the top level, okay, when you're looking for parts of the program, okay, you can say, well, I've got this whole problem. I bet it has an input part, a process part, and an output part. Okay, so that's a good guess about how to break it down. So here's the algorithm for a racquetball simulation. Print an introduction. Okay, here's the algorithm. What is this? This is pseudocode. Print an introduction, get the inputs, the probability of player A winning their serve, the probability of player B winning their serve, and N. Now, I just want to point out that I don't like the variable names, okay? First of all, they don't really follow the official Python style guide. A prob A with a capital A is a good variable name for Java, but a prob A is not a well-formed variable name for Python. So I think this guy's probably showing his Java roots or his C roots or C++ roots. Okay. The other thing is, they're so stingy. Prob A. It's like, type a little, why don't you? Okay, so um, now the letter N is often used in mathematics or sort of mathematical modeling as the number of instances or iterations. So, okay, I'll give you N. So simulate N games of racquetball using Prob A and Prob B. Print a report on the wins for player A and player B. Okay, well, interesting. Aside from print and introduction, we've got get the inputs, simulate the games, print the reports. Input, process, output. That's pretty good. So this kind of fits into that breakdown pretty easily. Is this design too high level? Uh, Whatever we don't know, we'll ignore for now. Okay. Is it too high level? No, I think it's just where we want to be at this point. Um, Whatever we don't know how to do, we'll ignore for now. It's a matter of um faith. You should you should believe that so long as you're trying to solve a feasible computing problem, okay, then at some point when you're decomposing this, you're going to break down everything to the point where it can be solved. And you either know how to solve it or can find a person or book to tell you how. Okay, assume that all components needed to implement the algorithm have been written already, and that your task is to finish this top level algorithm using those components. Okay, first we print an introduction. This is easy. We don't want to bother with it. So, um, what do we do? Do we simply print the introduction in our main? You can see that we're putting code into our main. Well, with a program that's this big, we probably want to factor that out into a function. So what he's done is he's called print intro, which I guess prints the introduction. And I just, again, I want to point out that the use of, uh, uh, for instance, the function name, this is a good method name for Java, but this is not a particularly well-formed uh, function name for Python. So I just want to warn you. If you're in my class, you probably would want to call this print underscore intro or introduction. I wouldn't even get angry with you for that. Um, so we assume that there's a print intro function that prints the instructions. Okay. What some people will do at this point when they're developing their program, they'll create what we call a stub version of the code. This is something that just is kind of a placeholder. So I would go down into print intro, and what might that do? Well, it might have one line in it that says print. I'm going to print the introduction here. Okay, that's it. With the idea that we'll come back and we'll make it work the right way later. The next step is to get the inputs. We know how to do that. Let's assume there's already a component that can do that called get inputs. Get inputs gets the values for prob A, prob B, and N. Okay? So, this is kind of interesting and very Pythonic. Okay? Uh, it is possible to return more than one value from a function. How does it really happen? Well, it really happens by what we return is at least implicitly a tuple. Okay, it's it's a data structure that in this case has three values. So functions only return a single value, but because that value can be a tuple, it can look like it returns 3. Okay, and you can think of it as returning 3, but the fact is that mechanically it's only returning a tuple. So here's what he can say. He's going to print the intro, and then he's got the variable prob A, prob B, and n, and they get populated by the function get inputs. Okay, so we get, once we split the tuple, which is done implicitly here, we get back those three values. Okay. Now we need to simulate n games of racquetball using the values of prob A and prob B. How would we do that? We can put off writing this code by putting it into a function. Now, and we're going to call that sim n games. So simulate n games, whatever the number of games is going to be. And then we're going to add a call to the function in main. So this is the programming equivalent of decomposing the problem. You kind of say, what would a piece look like here? Do I have to know exactly how to do it in order to define it? No, I don't. I have to know what the input is, and I have to know what the output is. That's all you have to know. We call that in the computer science-ish business, we call that the interface of the function. What are its inputs and what are its outputs? Okay, and so we just did one where we said that the outputs are prob A, prob B, and n. What are their inputs? Well, from the main function, there aren't any inputs at all. It's going to go collect those from the users. So really, no inputs, 3 outputs. All right? In terms of what the interface to the code is. What about print intro? Well, it doesn't return any values, so no outputs. We don't send it any values, so no inputs. Okay, so this is a great, we're going to accentuate the interface aspects of the code in another couple of slides. So now we need to simulate n games of racquetball using values of prob A and prob B. Okay? Where are we going to do that? Well, again, we're going to do the, we're going to do that in code. We're just going to call it sim n games. And we're going to call that function from main. If we're going to simulate the game by hand, what inputs would you need? The probability of A, the probability of B, and n. What values would you need to get back? The number of games won by player A, the number of games won by player B. So this, so the number of games won by each of the players, those must be the outputs from sim n games. So this is really program design thinking kind of boiled down to practicalities. Okay. First of all, you want to be able to describe the function sim n games in a way that makes sense, right? When the whatever words you're using to describe it, it's a sensible thing to do, right? Then you have to be able to explain what input you're going to have to give it, and then you want to be able to explain what output you're going to get back. Whether you know exactly how to do it at that very second uh, isn't material, okay? What you need to know is that you have faith that if you keep breaking this problem down, that you're eventually going to get to all pieces that you know how to do. Okay? I admit there's faith there. So now the program in main is going to look like this. Print intro, prob A, prob B, N is going to come from get inputs. Wins A and wins B are going to come from sim n games. Okay, now, again, sim n games can have two outputs. What's its real mechanical output? Well, it's a tuple with two values in it. But when we split that, we get wins A and wins B. Okay? And then what are the inputs? N, prob A, prob B. So, what information would you need to be able to produce the output from the program? Okay, you need to know how many wins there were for each player. These would be the inputs to the next function. Okay, so at this point, at this level, we're not going to uh, we're not going to we're not yet going to explore what it means to actually fill in the code for sim and games. Okay. What we are going to do is we're going to say if we call sim and games and we get these two values back, what do we do with them? Well, we print a summary. So we're going to have a function called print summary. And what's it going to take as input? Well, wins A and wins B. Pretty cool, huh? It's probably, I would say that uh, in terms of reading this code, in my mind, uh, print intro is like, oh, I can do that easy. Get inputs, I can do that easily too. Sim end games, not so sure how that's going to go. Print summary, oh, I can figure out how to do that. So most of the uncertainty surrounds sim end games. Okay, well that's okay. There's always going to be some part, usually the program, part of the program that's going to do the heavy lifting. That's where you're going to go. Oh, well, I'm taking it on faith. If I keep breaking this down, I'm going to come to a list of things that I know how to do all of them. Okay, so the original problem has been broken down or decomposed into four independent tasks. We just talked through the list. The name, parameters, and expected return values of these functions have been specified. The information is known as the interface or the signature of the function. So the interface or the signature of the function is what are the inputs and what are the outputs. And we're talking about the inputs and the outputs in terms of the call interface, right? So the higher level call, the main code, it's calling print intro, get inputs, sim end games, print summary. So we're saying what, if any, data does main have to pass to the function as it calls it, and what, if any, values are going to be passed back that can be used in the main function. Okay? And when you describe that for each of the functions, that is the interface of the function, sometimes called the signature of the function. Often, when people talk about the signature of a function, they're talking about the inputs only. But in this context, Zelle is talking about the inputs and the outputs. Having this information, the signatures or the interfaces, allowed us to work on each of the pieces independently. Okay? And it allows us to work on them independently. It allows us to worry about them independently. Um, in my mind, as a beginning programmer, I would sometimes get, I think, overwhelmed by all the worries of all the parts. Okay? One of the nice things about breaking things down and understanding their interfaces is when you're working on a particular part, you only have to work on that part, you only have to worry about that part, and you know what your responsibilities are. Okay? So you can relax and have fun and do your coding. For example, as far as main is concerned, how sim and games works is not a concern as long as passing the number of games and the player probabilities to sim and games causes it to return the correct number of wins for each player. Okay? Yeah. Does main actually care how you do it? Well, it probably cares that you do it responsibly. Okay? But exactly how you do it, it doesn't care. So now we're going to learn how to create a thing called a structure chart or a module hierarchy chart. And these have been around. Again, these were just coming into vogue when I was getting into programming over 40 years ago. And they're still valuable because they're a great idea. Okay? So, in a structure chart or a module hierarchy chart, each component in the design is a rectangle. So each component in this kind of a Python program is a function. So one rectangle per function. A line connecting the two rectangles indicates that the one above uses the one below. So it calls it. The arrows and the annotations show the interfaces between the components. What data gets passed in, what are the inputs, and what data gets passed out. Whoops, sorry, I went the wrong way. So this is, I think, a really good example of a structure chart or a module hierarchy chart. Okay, we have a rectangle for each of the functions. The top level one is main. On level 2, we have print intro, get inputs, sim and games, print summary. Okay. Now, remember that we talked about what the inputs and the outputs were of each of these things. Well, here on the structure chart, we can actually visualize what we were able to infer from the code. So the interface between the main and print intro, in terms of exchange of information as parameters in or return values out, there are no inputs and there are no outputs. It's just work to be done, and we're controlling the timing of it. Okay? Whereas with get inputs, there are no inputs that are sent to get inputs, but the inputs come back as the return values, prob A, prob B, N. In terms of sim and games, main has turned around and it has passed prob A, prob B, N to sim and games. And sim and games is sending the answers back in terms of two values, wins A and wins B. And then main is sending two values, wins A and wins B, to print summary, which is going to print them. Well, so does everybody draw hierarchy charts or structure charts for their designs? I think that beginning programmers should do it. Just for the heck of it, just sketch it out. More experienced programmers, they should do it when either A, they're trying to document the program, or B, this is a thorny kind of a program, and you've got to be thoughtful. Okay, one of the nice things about structure charts is you can kind of iron out a lot of the details um, on a piece of paper with a pencil and a big eraser, and you can save yourself a lot of coding time, right? So here we've gotten down to level two. Pretty much we know how to do everything but sim and games. That's the big deal, right? So we're going to take a break here, and we're going to come back in part two of the lecture and get down to the tough parts of this program. See you in part two.